Okay, so let's get started here with Unit 5. We're going to be working through slides 1 through 13 in this video um, and go from there. Okay, so kind of an overview for the unit here. This unit will discuss the sampling distributions of X bar and P hat. The key idea here is we're working with means and we're working with proportions here. So some of the big ideas here is we're going to have to differentiate between these two sampling distributions. So being able to read the context of a scenario or a problem and know which one we're working with, because the techniques will vary a bit. We're going to leverage Excel to generate random samples and compute some sample statistics. So working with the idea of truly randomly created data. And then we're going to go ahead and use those different things we've calculated there to estimate population parameters from said sample data. And that'll be towards the end of the unit where we really utilize that normal CDF command we've talked about before. Okay, so first thing to think about here is the sampling distribution of population means. So some of the symbology or notation we'll see here is going to be the population mean, which is represented as mu. So this is most often given to us in a problem. So just recognizing that when we're given that, that's dealing with the population versus a sample mean, which is what we'll be calculating. So X bar, that's the notation we'll utilize here for when it's a calculation we've done ourselves, whether that be by hand, with a calculator, with Excel, GeoGebra, whatever it may be. Population standard deviation is always sigma. That's just always what it is, just like last semester. Sample standard deviation, the most common one we'll see here is S, but I included the others a few times here just so we get used to seeing all the different variations that a textbook may utilize. Here we go, sampling distribution of population proportions. So just the symbology here again in notation. The rest is just kind of a further explanation here. So population proportion, we're dealing with P. P hat is something we calculate, it's from a sample. Standard deviation is still just sigma. And then again, kind of knowing the different variations of S with the P next to it. So this is all kind of review, just wanted to have it in written context for you guys to see. Okay, so how do we tell the difference? When we're working with means, the key idea here is that it's something we can quantify and measure. It's similar to what we've seen before. So some common examples of wording when we deal with a means problem is we're talking about things like weight, time, height, length, test scores, whatever it may be. It's really similar to what we discussed in Unit 4 and a lot of first semester dealing with that quantitative type data where it makes sense to add them together, divide, and we could find the mean there. The key idea here is that it's a literal number. It's not a chunk or a percentage. Whereas with proportions, the best way to understand these is through these examples here. So we can be given statements like 50% of you are taking notes. Obviously, it's always going to be higher than that. 1/3 of dogs prefer dry food. And again, I just made these up as I go. So we can be given a percentage of a population that fits a certain criteria, a fraction, or our proportion here. So 0.25 is the proportion of time most people spend sleeping each day. That one I feel like I kind of made up. It might actually be accurate there because 0.25 of 24 is about 6, right? So that one kind of makes sense. Again, the key idea here is these examples. We're seeing what is indicative of a problem that involves a proportion. It can't just be as simple as do we have a standard deviation, because both of these have standard deviation. Okay, so working with Excel. For those of you that have been in class, we've done this all together. So this video is going to be meant to just kind of highlight some of the key stuff we did and work through any kind of common misconceptions we may have identified there. Move this over here a bit. So I'm adjusting the screen resolution so you guys can see easier. All right, so Excel is going to be a big part about this unit. Now again, I've told you guys a countless amount of times in class, but save this example workbook. It's always nice to look back at a finished product for reminders of how to work through the various steps. Because going into next week, we are going to have a nice big summative project here working with Excel and doing something similar to what we've done in class. Okay, so I'm going to open up a blank Excel workbook and just work through this project. So I'm not going to keep referencing the slides here. If you're working on this on your own and you weren't in class, you'll notice that these slides give us an exact set of steps here. So it tells us each thing to do, each thing to type in. The one correction here was on slide 10. So if you're seeing this for the first time, go to slide 10. This number was originally something else. That was a typo on my part. I apologize. We'll go through how to get to that calculation here shortly, but it was 0.034. Okay, So the two commands we're going to utilize here to get started are going to be the average command, which is just finding the mean. So it finds the mean of certain values in a given column or several columns. And then this one here, norm inverse. So that's the command that we used first semester a lot to get those z-scores or the certain value that fits a given percentage, right? The random command here just generates a random number between 0 and 1. Mu is our mean, standard deviation is our standard deviation. So let's go ahead and see what we want to do first. Okay, so for our first scenario, we have scores on the final exam for semester 1 in Prob and Stats were normally distributed with a mean of 7. It was actually closer to 78, but I figured a nice whole number would be okay for this. And a standard deviation that was about 5. It was like 4.9 something. So we're going to utilize Excel to obtain 10 random samples of size 20. So 10 samples means like I'm pulling 10 different groups to look at. Size 20 means each of those 10 samples contains 20 pieces of data. So think to yourself right now, how many total pieces of data is this? If you thought of 200, you're correct. So since I have 10 samples of 20, that's 20 times 10 giving me 200. So the first thing we're going to do is in cell A1, we're going to input our command here. And then each of these is basically describing how to create more samples. So we'll do that all at once. So here in cell A1, I'm going to go ahead and click in here. And I type equals. So I have norm dot inverse. And then I open up a parenthesis, right? So the first thing I'm going to do here, I'm actually going to open and close those parentheses just to make sure I always have both. If it doesn't like that, that's okay. All right, so the first thing we type in is RAND with those parentheses. So what that does there, that RAND portion gives us a number between 0 and 1 randomly generated. So that acts as the probability to the left, if you will. So when we use the inverse norm command last semester, that just tells us where that z-score should come from. Now, what these next parts do here, so the mean from our example problem was 70, and then the standard deviation was 5. So this first portion of the command gives us a random number between 0 and 1. So if we think about how we found those z-scores, that's what that relates to. So it's picking the probability or the area to the left, the percent to the left. And then the 70 and 5 just kind of specify the distribution we're working with so that those numbers kind of fit its criteria. From this, we hit enter. And your number hopefully will be different than mine. Otherwise, it's really random, I guess. So yeah, we have our random number. Now, to go ahead and, this is column A here is going to represent our first sample. So our first of those 10 samples, and we want 20 in there. So instead of retyping this formula 19 more times, or 199 for that matter, for the whole thing, what we're going to do is just click on this little box here and drag it down through A20. And that'll populate with some more random numbers there. Now, I already have everything highlighted, so I'm going to go ahead and hold Control and press C to copy this. And then I'm just going to go over and paste it all through the columns up through J. So this is going to give me those 10 random samples of size 20. You'll notice each time I paste some new values, what's happening is everything's recalculating. So every time you edit an Excel workbook with formulas in it, each time you do something, it repopulates. So if you wanted to have a constant set of numbers, we'll go through later on in this course how to make those constant. Just something worthy of note that it will regenerate each time. Okay, so what we've worked through right now is go ahead and making all those 10 different samples of size 20. So in a few moments there, we've generated 200 random pieces of data from this distribution with a mean of 70 and a standard deviation of 5. Now, one thing with Excel is you'll notice here, since we copied this, it's got these, oh, by the way, to paste it was Control V, or you could just right click and hit paste. Trying to work on all the shortcuts here. So it's got all these little dash lines. If you want to get rid of those just to avoid accidentally doing something, just pick any blank cell, click in it so that that cursor there appears, and then hold Control and press C. It just copies a blank statement just so it gets rid of those weird dashed rotating lines. Okay, lastly, we just want to create a new sheet to work through our next one here. So to do that, on the bottom here, let me move this down so you can see. There we go. It's this one right here. So I'm on sheet 1 right now. This one, this circle with the plus sign, it gives us a new sheet. Also, if you haven't yet, make sure this is saved somewhere. Save it where you can find it, just so it's always easily accessible. Okay, so in this scenario, we have, according to bodybuilding.com form, we have 35% of adults age 18 and over regularly exercise in some fashion. randomly generate 10 samples of 20 adults each. So again, we think about this, 10 samples of 20, well, 10 times 20, that's 200. So I need 200 pieces of data. Now, if we think about our command here, that same norm inverse command we use to generate data for a distribution, we don't have a standard deviation in this problem. So let's go through how to calculate that. So our formula is here. Go ahead and clear that out. All right, so right here we have the standard deviation for a proportion is given as P times Q divided by N, and you take the square root of that. Now, depending how familiar you are with a calculator, you might be able to type this in all at once. I'm going to show the step-by-step approach just to make sure that parentheses aren't going to trip us up. So to do that, our P is given to us here. That's the proportion of the population, that 35%, that fits our given criteria. Here it's exercising in some fashion, but it could be anything. So to figure out P times Q, let's go ahead and do 0.35 times, well, Q is 1 minus P. Now notice I never put a percentage in here. I always convert it to a decimal first. So it'd be 1 minus, well then P is 0.35. We do 1 minus 0.35. Now if you know the answer to that offhand, you could obviously shortcut and go ahead and do that as well. So that gives me my P times Q. Now the next part of my formula is dividing by N. So we said there's 200 pieces of data because I have 10 samples of 20. So I'm going to take that 0.2275 and then divide it by the 200 from our sample. Lastly, we need the square root of that whole thing. So now I'm going to do the square root of 0.0011375. And again, the more decimals you include, the better. So 0.00115. Now, when we type this new formula, if you were to include all these, that's awesome. That's going to give you the most specific answer. But for sake of ease here, always include at least 3 decimals. So that's where this number came from. And again, in your notes, there's a typo there. It says something else. My apologies for that. But this is the correct answer we got here. So if I round it to 3 decimal places, it would be 0.03, and then this would turn into a 4 due to that being a 7. So 0.034. So we're going to use this command here to get our different parts for our proportion. So again, in cell A1, I'm on sheet 2 here. We have norm.inverse, our random command again, and then 0.35. So notice again, I'm not using the percentage. And this one was 0.034. So that's going to give us our command there to generate that random piece of data from this distribution. Just like before, we want the same size sample, so I'm going to go ahead and click, drag down to A20, Control C to copy, and then I'm going to go over into B1 here, Control V, Control V, Control V, all the way through column J. And the same little trick here to get rid of that those dashed copied lines. I'm just going to go ahead and click in any blank cell, hit Control C, and I'm good to go. So now we've created our 2 distributions. All right, here's the part where we're going to get our descriptive statistics. So pause the video now, take a moment and read through this. Try it on your own. Obviously mine won't literally pause, but you should, to try to get these commands on your own. They're pretty self-explanatory. But then you can restart the video, not restart, but like continue to play the video, and I'm going to show how to work through each of these steps. So we're looking to get our sample means and proportions, as well as our sample standard deviations here for each of these sheets. So I'm going to go ahead and start here on sheet 1. All right, so here I want the average, and then I'm doing A1 to A20, because that's my sample data. And then I want to get that for each. So instead of typing the command a bunch of times, I'm just going to go ahead and drag this horizontally and let go. And then I'm going to drag K a bit bigger here and go ahead and label this. So we're dealing with means here, so this is my sample means. And then down here, I'm going a bit out of order when we get our standard deviation, so STDV. Again, saying A1 to A20. Now I'm going to go ahead and drag that over, and then label that of sample standard dev. You can abbreviate, or you can type out the whole standard deviation either way. Key idea here is these are from samples, right? Now we're going to do the same thing for proportions. And again, the key idea here is whenever you're running a bunch of descriptive statistics here in Excel, always label, because otherwise this gets real dicey if I'm looking back at it later, right? So I'm gonna go ahead and label what these are. Okay, so at this point we've generated all of our data for our two distributions. We have some descriptive statistics, we have our raw data there, and 200 for each. And including the lecture from the first couple slides, we're still only at 15 minutes. All right, so that got us all through here. Okay, now we want to make some histograms, and then later this next slide just talks about what we're going to talk about. So we'll just make our histograms, and we'll do it all at once, all the different talking points we can have here. To do this, we're going to highlight all of the data, so all those different samples. Then we're going to click Insert on the, choose the all blue histogram, Insert Statistic Chart. I've tried to make these as to the point as possible. We're going to choose a histogram, and then we're going to edit it, give it a title, the basics. All right, so I'm on sheet 1 here. I'm dealing with my mean, so I'm going to highlight all the data. Now notice I'm not including the means or sample standard deviation. We don't want those in there, just our data. So then I go to Insert, and then right here, dead center over here, is a blue histogram. So let's click that. Again, it says that Insert Statistic Chart, which I included in the notes there. And we want this first one here, so just your basic histogram. Now, the first thing we're going to do is change the title, because any good graph should at least have a corresponding title. So here we're talking about semester 1 final exam grades. And you could always get more specific there if you wanted to, but for our purposes, that's fine. Okay, now there's a lot of extra we could do here, which we'll work more with in class. I'm going to encourage you guys during your project portion of next week to go ahead and do a little more, change the color. But for today, I just want to worry about the interpretation. So when we're looking at this data, first thing we're going to talk about is the shape, right? So if I'm following this curve here, so I'm kind of drawing a nice curve over it, it's pretty close to normal. Like if this were me, I would say this is normally distributed because I can see the majority of my data is kind of in the middle here and it follows that curve. A little bit of outlier behavior up here. Perhaps you might want to call this skewed to the right because there's a lot more data on the left than there is on the right. This one, again, if I were grading this on an exam, I'd be looking at your individual Excel spreadsheet you've submitted and kind of looking at those different portions of it. But key idea here, the most common interval here would definitely be this one here, right? So if we're looking here, we could definitely see that this one would be the most common. And again, it's a frequency histogram, so it tells us in this interval we have 10 values there, where there's 6 in here, so on and so forth. But again, the idea of all we're doing so far is being able to determine shape. We'll get into more specific stuff as we move on. All right, so let's go ahead and get our histogram in the same method here for sheet 2, and then we'll go back and talk a little more about the data we found. So I'm going to highlight, insert, here, histogram. And then our title for this one, we're talking about adults who exercise. So proportion of adults who exercise. And again, your titles can vary a bit here. I'm just kind of summarizing. And again, it gives us the frequency here for each interval. So in this proportion, in this interval, and this interval, it gives us our various frequencies as well. So if I was describing the shape of this one, not quite as normal. We see a noticeable increase over on this side. But again, it's still fairly normal. Distinctively skewed behavior is much more noticeable. But again, as far as grading on an exam goes, I'm looking at what you've submitted to me and basing my decisions off of that and how you explain yourself and how you justify your conclusions. So for this one, I'd probably take normal, or I would perhaps take skewed to the left because the majority of my data lies on the right. All right, so some other things we want to talk about here would be, go ahead and get rid of some of this. And again, please save this thing somewhere so you have it. Let's go ahead and look here. So if I'm looking at all of my sample proportions, right? So from our problem, we said 35% was what we knew about the population. For my sample calculations here, if I'm looking at all these numbers, all of them seem pretty close within a reasonably small margin here to 0.35. That makes sense because it's not always going to be exactly the same. In fact, it'll almost never be exactly what you expect. But when we have a sample from a population, all of those samples should be close. So if I were to take a sample in real life, say we weren't doing this with random data, and let's say I said, okay, I know that 35% of adults do this, and then I took a sample and it found that 80% of those people were doing that, that wouldn't make sense. That would tell me that, okay, two things here. Either my sample is really, really biased, meaning like everyone there happened to work out, or I did something wrong in my sample and that this isn't really indicative, right, of the population, and maybe I should examine the population characteristics. I definitely need to resample as the sum up, right? So either I'm really wrong, my sample is biased, or the population is wrong, which is rarely the case. So whenever we get something that's totally different from our population, we want to examine how we got that sample. Similarly here, we set our standard, sorry. Oh boy, it's Control Z, that one. There we go. If we go ahead and look here at our different sample standard deviations, and again, you see that this regenerates each time I touch something. It was 0.34 was our sample standard deviation, or our standard deviation we calculated, and we can see all these again are close. So again, as long as they're close, it makes sense. Same thing here. We go ahead and examine our sample standard deviations. Here the average was 70. So from each of our samples, we're looking close to 70. Yes, those are all reasonably close to 70, so it makes sense, right? So if this were real data I calculated, I would say that they supported the conclusion that the average was 70 because all my samples are pretty close. Same thing with sample standard deviation. We said we wanted 5, and all of these came out pretty close to 5, so that makes sense as well. So some of the key characteristics here are what this is used for is we can go ahead and let's say I gathered a literal sample of these things. I could see if the values are making sense by doing these simulations to see what I could expect. So as I'm looking here, I see a lot of scores in the 70s, the 60s, there should be some, I can't rapidly find with my eyes, but you might have one in the 80s, right? Here's one in the 80s. But the point being is that if the average is 70, you think that everything should be somewhere around it. So I have a high value I see over here of 83. It looks high, but again, since it's been randomly generated, I see that it's not an impossibly high score. Now, if I were to see something like a 10% in here, that would definitely be an outlier, right? That doesn't make sense with the rest of my data. Same thing here in sheet 2. We're looking for things around 0.35. We could see some things. Here's a 0.43. That seems a bit higher, but again, it's not totally unheard of because again, it's within our random sample here. It's not a totally impossible number. We might see some things in the 2s, so like here's a 0.29. Yours might be slightly higher or lower. That's the idea of randomness. But again, this gives us an idea of what typical data in this distribution would look like. So the key ideas and takeaways here are how to model data, how to generate random data, and just kind of predicting what a distribution should look like. So our distribution here would definitely be, now this is a good example of a skewed one. So this distribution here, this is definitely skewed to the right because like all of my data is on the left. So since the majority of my data is on the left portion of that x-axis, this would be skewed to the right. If I mirrored this, so if I kind of flipped it and these two bars were over here, and these two over here, then it would be skewed to the left because the majority of the data is on the right. So with that, you should be all good. Kept the video under 25 minutes. Pretty impressive, I must say. And we finished through slides 13. So we went on here. This is all the stuff that we talked about, right? All right. Okay, so we're working through the Excel data activity here that we started last week on Friday. And again, it's due Thursday, January 17th. Check dates right. Yes, the 17th. Okay. So I deleted everything, so we're just going to kind of start from scratch here on working through this. First thing we can do is we can go ahead and delete this final exam grades tab just to make the project a little more time manageable. We're going to go ahead and get rid of that. So if I want to delete that, I'll click on it and then right click and choose delete. And just confirm your choice there. So that one's gone. All right, so first thing we're going to start off here is my example. This is where we're working with these semester grades. So we'll notice the format here. I always put the real column first, so the actual data, as opposed to the generated. Then we have our calculation space here, the means and standard deviations. So we'll work through this one together, which we've already done in class, as well as talk about the absences here, and then walk through the guidelines on the your example portion of this project. So first thing we're going to do is let's go ahead and do some calculations here with our real semester grades. So if I take a look, the data goes from cell A2 all the way down to A33. So if we want to find the mean for that, we're going to go ahead and use, if I click in here, equals average, and then it's A2 to A33. Press enter, and we'll be good to go. So when you guys do these calculations with the quote-unquote real data, your number should be the exact same as mine. For the standard deviation, here's our command, stdev, and then A2 to A33, so the exact same range. And we get our data there. Okay, now we need to generate some data. So to generate it, we've talked about using the norm.inv or norm inverse command. Our first input here is going to be random. That gives us the probability, so it'll regenerate each time we click on it. And then we put in our mean, which we calculated. And again, depending how wide your cell is here, you might have a few less decimals. That's okay. And then our standard deviation. And just make sure you use at least 3 decimals there. Okay, so now that we've got our random data, we're going to go ahead and drag it on down here. So we use that lower right box there, left click, and then drag down. Remember, if you're clicking the lower left box, it functions as a copy and paste command. So it brings everything down. Now, with your Excel sheet, you are probably getting more decimals here. So the first thing we're going to do is talk about how to format these cells. So let me go ahead and pause the video. What I did was just basically get mine looking how yours is going to look when you first do this. So when we think about semester grades, we typically don't have 8 decimal places when we display them. Here I had them rounded to 0 decimal places, but let's go ahead and make these say 1 decimal place just for ease of reading and to look a little more what we're used to seeing. So when we want to format cells, we always want our data to make sense with the type of data we're looking at here. So for these semester grades, we're going to go ahead and change that. So to do that, we want to right click here on the column B, and then choose Format Cells. So when we get here, it'll default to the general thing. What we want to click on is number, and then we're going to change the decimal places. So let's say I just want it 1 decimal place. I could change that to 1 and then click OK. And that'll actually go ahead and fix that whole column for me. So it just rounds to 1 decimal place for us. All right, the next step here is we're going to go ahead and find out some data about our generated stuff. So under here, I'm going to again do the average. And this time, I'm looking in column B. So it's the same length, so B2 to B33. And then for standard deviation, same thing, B2 to B33. Now, we'll notice that each time we want to, we can regenerate both these 2 numbers as well as this entire column. To do that, click on any blank cell. So double click with the left side of the mouse, and that gives us this cursor here. If we press enter, we'll notice all those cells recalculate. So each time I do that, it happens over and over again. We'll use that feature later on as we analyze the graph. Now, before we can make some conclusions about our data, we need to figure out how we can visualize these data sets. To do that, we're going to utilize histograms like we did in last week's notes. So the shortest way is you just click on the top of the column here. So if I want to do for my real semester grades, I'll left click on column A, go to insert, and then we want this one right here. So this blue histogram. So we'll click it and we'll choose the first option there, so histogram. And then I want to make sure I title this so I don't get confused in which data is which. So I might want to title this real semester grades. And then to get our other one here, so then our generate it, we'll left click up here. And again, go to insert, we're doing the same thing. And then I'm going to go ahead and move this a bit and title it as generated semester grades. Oh, didn't mean to do that. Remember, Control Z is to undo things we accidentally did, like I just did there. Okay, So now as we get into the conclusions, and again, if you want to edit things on the graph, this whole menu over here, formatting plot area, I'm going to leave that up to your guys' experimentation to kind of make these graphs look a little different, a little better, whatever it is. Again, this is kind of the bare minimum I'm looking for here. But again, I encourage you to experiment with that and try to make yours look better. I mean, definitely like make them a different color. So if I click here, let's see. Trying to see where the color option is. Menus are actually going to give us some more in-depth stuff, so we could change the borders, the fill. If you just want general color changes, easiest way to do it is just click on the chart you want, and then if you go up here to change colors, you could pick a different theme. So if I chose, say, this one, I get green or orange, vice versa. So again, just a bit of customization up to you how in-depth you want to get with that. So the last thing we need to do here is go ahead and make our conclusions. So the conclusions are, we're going to do these in like a 3-step format. So step 1, we're going to talk about the generated data. So when, spelled a lot of stuff wrong there. When analyzing the generated semester grades, and again, you can use synonymous terms here. So that's going to be kind of my first prompt. My second prompt would be when analyzing the real semester grades. And then lastly, when comparing the 2 distributions. So those are kind of our 3 prompts there that go through each of those. So we'll use each of these as kind of our guides. And that's how we're going to analyze each of these questions. So for the first one, when analyzing the generated semester grades. Now, first off, when we work with the generated semester grades, we're using a command that forces our distribution to be approximately normal. So this is actually a pretty good graph here, but let's say I want to change it a bit. So I'm just going to regenerate this data. So click in any blank cell and then hit enter. And you'll notice that graph is going to change. So you want to play around with it a few times just to get it to look as normal as you can get it to. So I'm going to do this a few more times here. So again, it takes some trial and error. That was actually pretty good. I should have kept that one. All right, so I'm going to use this one because this gives me a pretty normal scenario here. You'll notice that when we change these decimal places, it's a lot easier to read on the graph, which also helps. All right, so I'm going to talk about this one now. So I can get it, I can see it now. It's approximately normal, right? Some of those random outcomes were a little less normal, so we want to keep generating until we get that. As I'm seeing this now, I see I have one bar that's distinctively higher than the rest. In some cases, you might have 2 bars in the middle that are higher. That's okay. You can use both of them, as we did in a couple class examples. Here, though, I'm just going to use this bar because I notice it's distinctively higher than all others. So when analyzing the generated semester grades, the majority of data is between, and I'm just going to talk about these 2 bounds on here. So mine is 60.5 and 76.5. Now again, yours will likely not be the same. That's 100% okay. I'm grading it based on what you have, not what I have. Now let's look at those real semester grades. When analyzing the real semester grades, the majority of data is between. Now this one, it should look exactly the same as mine because again, we talked about these being constant values. They're not regenerated. So your graph should look the same as mine. All right. So for here, if I'm looking, the majority of my grades here are between 50 and 66. And again, you'll notice every time I click on something, this is going to regenerate. So again, I'm going to base the interpretation off of what you have on here. So again, with the regeneration here, I'm basically looking at your conclusions here. I'll look at the graphs to see that they exist, but the conclusions I'm kind of going to grade independently and just make sure that they make sense. Again, like this one, the real semester grades or any real data for that matter won't be changed. But this one, obviously, if you accidentally click or something, it'll change, and then those numbers would be adjusted. But I promise you, I'll grade fairly on that. Okay, so lastly here, we've talked about each of our graphs with the majority of data is between. Now what we want to look at is this here. So we're looking at the actual mean from our data. So here I had 68.2 and some change here. So I want to see which one of these intervals, or possibly both, actually contains that data. So for the first one here, we have our interval. We had between 60.5 and 76.5. So the mean is between there. For our second one here, it looks like it's between 50 and 66. This is really skewed. So, and the mean was actually outside of that first bucket. So it would have been this one here. So in this scenario, I think that the generated data actually does a better job of displaying the true outcome here of what the grades are going to look like. So that's what I'm going to kind of summarize here. So when comparing the two distributions, I believe the generated semester grades more accurately portray the data since the interval contains the real mean. Now, we could also say here, you could say the other one, the real one isn't as good because it's skewed, or again, there's a variety of ways here. But when we generate things from a distribution and we utilize a normal command to do so, we're always going to have it kind of gets rid of all the outliers. Like we could see here when we keep regenerating this, it will continue to have those outliers. There's a few up here, right? That wouldn't make sense. You can't get above 100. And we'll see that a little more in the next example here with absences. But again, this is kind of the three parts I'm looking for. So as far as the rubric goes, I'm going to have 25 points for, let me bring this up for you guys here. Give me a second. It's going to be, I'm looking at two tabs here. So I'm going to look at the absences tab and then the your example tab. So the things I'm looking for, it's going to be 25 points for the graphs and 25 points for the conclusions. So graphs, generating these are a combination of all of this work. So I'm looking at all your calculations, and a good way to test that to see if you've done it correctly is I can click on any cell here, I can see a formula, press enter, and then everything regenerates. So that's how I'm checking that. I'm looking to see that your graphs have titles, that you've changed some colors, that you've made the numbers make sense here, so that I don't have, if I'm talking about a shoe size, I wouldn't want 8 decimal places, right? So again, we'll do a little more of that, making sense of our formatting there. So I'm just looking that your graphs exist, that they're well formatted, and that they're titled. And again, try to change the colors, perhaps change up the background a bit, whatever it may be. I'm also going to be looking at when you submit this, before I do anything else, that the graph looks approximately normal. So I want to see that you've regenerated a few times to get a good normal distribution there. And then in your conclusions, I'm looking for the three parts. So I'm seeing that you're talking about the generated, the real grades, and then you're saying which one you think is better and why. At this point, we haven't been given enough tools yet to really definitively say which one's better. So I'm really just looking up for interpretation. I'm looking that you have some justification for why you think one's better than the other. We might talk about the shape, if one's skewed, if one's not. One might contain the mean. As we'll see in the next example, sometimes that generated data actually gives us unrealistic answers. It gives us values that don't make sense. So we'll see that there as well. All right, so let's go through absences here. This one is for a grade, but I'm gonna at least get you started on it. So I'm gonna move a little bit quicker here. So what I'm gonna do right now is pause this video, and then it'll pop up with all the answers. Basically, I just wanna see that you can do that on your own. If you look at my example, again, if you click anywhere, the formula is utilized, you can see. Real quick thing, just a bit of advice. If you look down here, if you're trying to copy and paste some of these formulas, make sure you change it because this one has 51 values, whereas our previous example only had 33. But other than that, it's formatted the same. So I'm gonna go ahead and pause right now and do some calculations here, and then we'll talk about interpretation. Taking a quick look here. All I did was the same steps as before, so I calculated my mean and standard deviation, generated some data, and then the mean and standard deviation for my generated data as well. Now, when we look at this, so this is where I'm talking about making sense of the numbers. Here we see that this doesn't make a whole lot of sense. If I'm talking about absences, and we think of you're either here or you're not, it's kind of a binary thing. So it's only going to be whole number values. So again, this excessive amount of decimal places really doesn't make sense. So first, we're going to format that. So again, this is what I should see in your example as well, is I should see some kind of logical formatting. You don't necessarily need to explain it. If you want to, you could put that in there, like I first edited the data, the generated data, so that it was whole numbers or decimals, whatever it may be. Like if I was doing an example with money, I would probably want to make it only 2 decimal places, because when we think of money, it's just 2 decimal places. If I was going to do shoe sizes, I would maybe do 1 decimal place, but you could do whole numbers for that if you wanted to. All right, so again, to do that, we're going to right click here on column B and then go to Format Cells. And then we want to go to number. So if I want to make it whole numbers, I would want 0 decimal places. So I'm going to put 0 and then click OK. Now, upon inspection of this data, we see we have some stuff that's negative numbers. Now, the reason why that is because if we think about our distribution here, so we're saying there's a mean of 13. And then my standard deviation is also 13. So it means essentially we're really going to see a lot of that number line involved there. If we think about how that looks, so if I want to go out, you guys don't have to do this part. I'm going to pause. I'm just going to show you in GeoGebra what that distribution looks like. Brought open GeoGebra for our visualization. So here we had a mean of 13. I'm just going to round for the sake of this, and then standard deviation of 13. So if we look at that, and we look at our general picture of the normal curve, so our mean is right here at 13. If I just go one standard deviation each way, I'm already at the value of 0, an upper bound there of 26. So if I think about that, that's 68% of my data. If I go a little farther out each way, right, I can see that I'm still within that, under 1 probability, and I'm getting a lot of negative numbers in there. So we might talk about how that affects our data as well. All right, so from here, we'd go ahead and generate our histograms. So when you're making your conclusion here, again, we're going to follow the same kind of 3-part prompt. You might say something like, well, the generated data doesn't work that well because it has, it's going to have those negative numbers in there. So even though it's normally distributed, a lot of the data values aren't actually possible. So again, that's something that you could potentially involve in that 3rd step of the conclusion where you decide which one's better. Okay, lastly, going to your example, just kind of giving you a brief synopsis here of how to complete this. So let's say I was talking about how much people would pay for coffee. So I would put real price of coffee. And then I would change this to generated price of coffee. So you want to make sure you include the title so I know what your data is about. I'm not asking for a huge write-up, just change the titles for me. And then you'll change these as well, so label them according whether it's the real or generated, your prompt there. So these you'll have to manually enter, and again, you could either use the data we collected first semester, some of the quantitative questions you asked, or you could just survey your class, survey some people around you. Try to get at least like 20 pieces of data there. Ideally, more is better. And then you'll go through the exact same steps as we had before. So with that, kept our video under 20 minutes here. You should be good. Again, this will be due on Thursday in class, and then we'll do some random little presentations specifically about your example slide here when we get into that on Thursday and Friday. All right, so today we're going to actually go through slides 13 through 21 in this video. So we're going to go ahead and finish up our notes here for Unit 5. So we've gotten through everything with the different Excel simulations. Now we're just going to kind of summarize how to look at those statistics. So a lot of this is meant to be reviewed because we've already done it in that take-home quiz. So first thing I'm going to do is kind of summarize what we found here in our sheet 1. So for this Excel file, you want to look back and find the one we did in our notes. So it was way back about almost 2 weeks ago now, where we worked with those sample means, sample proportions, generating our data, and working through it. Here I'm looking at sheet 1. I called mine Unit 5 notes, not sure what you called yours, but yeah, you should be able to find this. Okay, so if we look here, we have our 10 samples. So these are my 10 different samples, right? Of size 20, because in each one I have 20 different values. So here's the command, just a reminder of what we used, right? So our mean from this population was 70 and standard deviation 5. So we did create some histograms. We've already talked a whole bunch about shape of that. So for the sake of time in this video, I'm going to kind of move through some of the stuff we've already covered. So let's see what kind of questions we got here. This one should be simple. Sample mean for each of the 10, right? We already calculated that. We use the average command. I labeled those are my sample means. These are my sample standard deviations. And again, I bold texted it just to make it easier to see, but not totally necessary. Histograms we've already talked about, and then what we expect them to be. We always expect them to be what we sampled from. So if I know that the mean is 70, I surely expect my sample means to be pretty close to 70. And standard deviation was 5. So similarly, I suggest, or I'm expecting these to be pretty close to that 5. So we see we have like a 3.6. That might be a little low, but not terribly low. The idea is that when we draw from a population, we expect our samples to look pretty similar. All right. Okay, so computing the sample mean, sample standard deviations. We've already done this. And yeah, they are pretty close. So they're always going to be pretty close just by the nature of the formula we're using. We're telling it where to look and what numbers to use, so they're always going to be pretty close. Now, occasionally there might be values that are a little high or low, and that's totally fine. If you get that answer on an exam, you insert it at your work, you could talk about it. Be like for example, let's say I was looking at mine, and maybe I felt that this 3.6 right here was lower than I'd like. And I'd say, hey, look, for my population here, it was supposed to be 5, and this one was 3.6. Maybe if I was going to do some simulations, I wouldn't use that one, right? So maybe I'd regenerate a few times here until I got rid of those, lower 3 numbers. So maybe this one's better. But then again, maybe I might have something in the 6s, and that might look high to me. Again, it's all a matter of just looking at your data and seeing what you can find. Okay, going into the theoretical probability. What we're going to do here is this is going to relate back. So when we think about theoretical probability, this is semester 1 where we dealt with normal CDF. So normal CDF gives us a theoretical probability, whereas in actuality, we know when we calculate things, when we do samples, when we generate samples such as we've done here, it might not be exactly the same. So just a review of this, right? So we're dealing with means, and we're dealing with a theoretical probability. So when we sample from the mean, this is going back to normal CDF. Essentially, we want to figure out that we're looking greater than 70. So remember, this also might be a bit of a typo in your notes here. So this 70 and this 70 actually said 78 in your notes. That's my fault, my apologies. So if you want to go and correct that now, if you have not already in class, that'd be great. But let's go ahead and look through that. So for this one, here we're going to use the normal CDF command, which we'll talk more about later on. So here I'm just going to kind of sketch it out. So this would be normal CDF. We want greater than 70, so 70 is our lower bound, our upper bound, acting as infinity, 10 to the 99th power, our mean 70, and our standard deviation is 5. So if we went through this in a calculator or GeoGebra, we'd get about 0.5. So that's what we're expecting. We're expecting in our sample that the chances that it's higher than 70 is about 0.5. Now we're going to compare that to our practical or our simulated results here in this next question. So what proportion of the 10 random samples have a sample mean greater than 70? And then we're just going to comment on if we think it's close or not. So if I'm looking here at my sample means, I'm just going to zoom in a bit. Here's my sample means. We said there's 10 of them, right? Because there's 10 different columns. So count in your head right now. How many of those are greater than 70? Okay, so we have 1, 2, 3, 4, 5, 6. I have 6 of those 10 are greater than 70 because the numbers are bigger than 70. So for my answer here, I would have 6 out of 10, so about 0.6. Now, depending on when you generate your data, that doesn't look like a 0. Sorry, let's get rid of that. 0. Maybe you got 0.7, maybe you got 0.3, maybe you got 0.4, or maybe you did get exactly 0.5. This is going to be something that when I'm grading, I'm going to look at the data that you generated and compare it to your answer. So I'll just manually count through this and calculate this for each of you. So sadly, this is not an answer key multiple choice type test. It's you actually showing me you know how to answer this question. So of those 10 samples, what proportion of them is greater than 70? So if I was commenting on this, I'd say, yeah, these are pretty close. Anything within like 0.2 is probably pretty close for this example, just because we're bounded between 0.1 and 0.9, or 1.0 technically and 0. But again, I'm just looking that you can comment on this. So here was our theoretical value. We expected 0.5. In our sample, we got 0.6. So a little higher. Again, this is just showing that we can compare between a theoretical and a sample. And if you're feeling totally lost right now in normal CDF, we've done it first semester and we're going to review it as well here. Okay, so let's look at our spreadsheet now for what we did with proportions. So on mine, this was on sheet 2. So here's the command we used up here. So our proportion from the population was 0.35, and then we calculated our sample standard deviation to be 0.034. Again, try to always include 3 decimal places in those at least. More is always better, but 3 is the bare minimum I'm asking for. So here, I'm going to zoom in a bit. So we calculate our sample proportions, again, using the same average command as we'd use with means. And then our sample standard deviation, again, the same as we did with means. Okay. All right. So if I'm looking through this here, let's see what kind of questions we could expect to answer. Determine p hat. So here the vocab is knowing that p hat just means sample proportion. So there they are. Sample standard deviation, same thing for p hat. So that's just being able to identify these numbers here. And again, labeling always helps. That'll help you when you're going back and looking at it. We already talked about shapes of the histogram, so skewed left, skewed right, normal. A couple of us actually got bimodal in our examples, which was unique. Usually those don't exist. So we did talk a little bit more in class how oftentimes a bimodal distribution kind of indicates that we should separate our population into two groups there. Okay, and then talking about the theoretical results. So again, just saying, are these close? So maybe in this question, I'd say, what proportion of the samples here? So what proportion of these sample proportions are greater than 0.35? So I'll take a moment now and figure out what proportion of those are greater than 0.35. So if I'm looking for greater than 0.35, let's see, no, 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 yes. So 1, 2, 2. So my proportion here would be 2 out of 10. And we're not going to do any of the theoretical stuff yet because we haven't technically talked about it, which is what we'll get to next. So again, about half of your test is going to be variations of creating distributions in Excel, talking about their histograms, and doing these sample statistics with them. Okay. All right. Out of simulation, back to estimation. So we'll not always be working with simulations. Many times we need to make estimations of population parameters using sample statistics. So a lot of time we have some information up front, and we just want to make some general conclusions about what we'd expect. So we don't always have to go the simulation route. These type of scenarios or problems relate back to implementing our normal CDF command. So again, very heavy here on GeoGebra or calculators. We will go through in class how to utilize Excel for everything, just because I find it interesting, and it might be a useful skill for some of you looking to major in, things like accounting, business, marketing, because those are very Excel heavy. Not very often do we whip out a graphing calculator type thing. So I will go through that in class, but for the sake of this video, I'm going to stick to GeoGebra and the calculator for doing the normal CDF. Okay, so we're going to start off here with example 1. So we have the following scenario. According to a survey of my students from last year, 38% of students preferred caramelized coffee as opposed to other options. Suppose a simple random sample of 200 students is obtained. All right, part 1 here. Are we dealing with means or proportions? So if I'm looking at how this problem is presented, I see that my figure or my statistic is given as a percentage. So that's a key indicator if we're having a percentage, a decimal, a fraction. We're always going to be dealing with that realm of proportions, whereas our means problems are typically stated as average, expected value, mean, right? We're used to seeing those a lot more. Okay, so when we deal with proportions, sorry about that, our first key idea is this. Our number line for proportions. So when we talked about means, we went from negative 10 to the 99th to 10 to the 99th, acting as zero or acting as negative and positive infinity. When we're dealing with proportions, we actually want to have our smallest possible value be 0 and our largest possible value be 1. So that's that key step there of identifying what type of problem we're dealing with. Okay, sampling distribution of p hat. Here what we want to do is just like a formal step of saying what the p we're working with is, and then what's the standard deviation. So here we're told p in the problem is 38%, so we're just going to go ahead and throw it in there at 0.38. And you're going to see me just use p hat for that. And then for our sample standard deviation, just the notation, I'm going to use S with a P next to it. So the S represents the sample standard deviation. The P just denotes we're coming from the realm of proportions. Okay, so this formula, right, I'm just going to scratch it down up here. So S sub P, we did P times Q, and we've done this before. You've done it on a quiz, actually, so we should have it down by now. So I have a P of 0.38. My Q is equal to 1 minus P. So that would be 0.62. And then my N here, we said 200 students. So that's going to be my N there of 200. So we've talked a lot about how to type this into multiple steps. I'm just going to go ahead and do it all at once just for the sake of time here. And again, the input here is going to vary based on what type of calculator you're using, hence why I've taught it to you guys in the step-by-step format in class. All right, so to 3 decimal places, looks like I got 0.034. So that's just describing our population there. So again, whenever I ask you to describe the sampling distribution, I need you to tell me the proportion you're dealing with and the sample standard deviation. Okay, so we have in this random sample of 200, what is the probability that less than 35% prefer caramelized coffee? Okay, so if we're looking up here at our number line, so we're dealing with 35%, so it's 0.35, and I want less than. So less than signifies to me I'm looking at this left side of the graph, because those are the numbers that are less than 0.35. So if we're thinking of our normal CDF command, I'm going to sketch it out as that, and then we'll go ahead and do it as well in GeoGebra and in the calculator. Okay, so I want normal CDF because I'm finding a probability. My lower bound is 0, upper bound is 0.35. My expected value here, my P is 0.38. And my sample standard deviation is 0.034. Let's go ahead and just sketch out the next one as well, just so we have all the calculators open at once, right? Different color here. Okay, for our next one here, we want in the sample of 200, we want more than 40%. So more than 40 would signify going to the right. So here I'm looking to the right of that number. Again, I'm finding a probability, so we're at normal CDF. Here my lower bound is 0.40, upper bound is 1, and then my P and my sample standard deviation just come from the same context as prior to this. Let's go ahead and take a minute. I'm going to pause, get those down. Okay, so let's go ahead now and solve these. So I'm going to start with the calculator. Again, that's just more of a typical college methodology for how professors will expect you to solve these. So my normal CDF, and then I'm going to go and type 0, 0.35, 38. Oh, what did I type wrong? Let's go and get rid of that. Okay, so lower bound, 0. Upper bound, 0.35. Mean, 0.38. And 0.034. There we go. So that probability, again, at least throw me 3 decimal points. If it were a multiple choice question, a bit easier to pick out. But again, there we go for that one, right? Doing our secondary one here in the blue. So I'd have lower bound of 0.4, upper bound of 1, 0.38, and 0.034. And we're good to go there. So we found out our probabilities of, again, being that less than 35% or more than 40%. So if you want to pause the video at this time, if you're writing those down, I'm going to pause as well and get GeoGebra opened up. So into GeoGebra. For this one here, so I'm just going to put mine to the side so I can kind of see what I'm typing in here. All right, just to review, to get to the probability calculator, we click on these 3 horizontal bars in the top right, go to View, and choose Probability Calculator. We really don't need the graphics, so I'm going to get rid of this portion of mine. This is always nifty if you want to use this calculator, so I'm going to leave that there. Okay, so step 1, we're dealing with a normal distribution, so we could stay in normal for this whole unit. Just to review, these 3 signifiers. This is less than, between, greater than. Again, we've done this all first semester, so it's just kind of, getting the dust off type thing. Less than, between, greater than. So in this problem, for the first one here, we're looking at less than 35. So I'm going to go ahead and use my less than. My mean for this problem is 0.38, so 0.38. And my standard deviation here is 0.034. Okay, now we want it less than 0.35. So I'm going to go ahead and change this to be 0.35. Oh. Press enter, and we're good to go. So again, if you're sketching down what we're typing in here for GeoGebra, go ahead, pause the video at this time, and get that down. You'll see we got the exact same answer. All right, for the next one here, we're looking at more than 40%. So I'm going to choose my greater than here. My mean and standard deviation were the same in this problem, so I'm just going to hit enter. Second here. One second, mine is not updating. There we go. So I'd hit enter up here as well. If things don't change, again, kind of make sure you type in each thing and hit enter. And we can see we're good to go there, right? So for the more than 40, we got the exact same answer here of 2782. This one was a little longer, but that's just the rounded version. So we're good to go there. So again, nothing really different here. It's just kind of changing those upper and lower bounds as we need. All right, let's move on to our next slide. Okay, so we have the exact same sample as before. So I'm just gonna kind of jot down my sample standard deviation here so I remember it. Let's make sure that's right. Yes, 0.034. Okay. So same scenario. We're saying, would it be unusual? So kind of the vocab here, we're going to use anything less than a 5% chance as being unusual. So in 90 or more students preferring caramel iced coffee. So let's think about what we got here, right? So little different, but again, kind of the same type of problem. So this should look similar to what we did with binomials. The only difference is in this unit, we're actually going to use the normal curve to work with our binomials as well to kind of generalize things a bit here. Okay, so we want 90 or more. So I have 200 in my sample and I'm looking at 90 or more. So I had to figure out what proportion that is. So you might want to show your work elsewhere. I'm just going to kind of do it all here so we can see it. So I'm between 0 and 1 because I'm dealing with proportions, right? Okay, now I want 90 or more. Now, we need to get this to be a decimal. So figure out what proportion 90 is of that 200. We're going to divide. So anytime we're given this context of a number of people, but yet we're dealing with proportions, we want to think about getting that into a proportion. So I'm going to go ahead and divide that here. Now, these might not all come out as nice numbers. This one will, but they might not always. So I'm just going to leave it as a fraction like that. And I want it more than, so I'm going to go ahead and look to the right. So for this command here, we have normal CDF. My lower bound is going to be that 90 out of 200. And again, you could simplify. I'm just trying to avoid any rounding errors. My upper bound is 1. We still have 0.38 for our P, and then 0.034 here. So go ahead and pause if you get anything down. I'm going to start erasing now. All right, for our next one, would it be unusual that this sample results in 70 or less? So here I'm looking at 70. And again, to make that into a proportion, I divide by how many are in my sample. And we want it or less, so I'm looking this way. So normal CDF. That's 70 out of, oh, my bad, going to the left. So I want 0 to be my lower bound. Upper bound is that 70 out of 200, 0.38, and then 0.034. And again, we type those into a calculator. GeoGebra doing the exact same thing. And you could literally type these in just as I've shown here. Just do 90 divided by 200. The calculator or GeoGebra will automatically update to that value. So the key idea here is you're saying if it's unusual. So if I get a number that's greater than 5%, so remember 5% is a decimal, is 0.05. So if it's greater than that for the probability for our answer here, if we get something greater than 0.05, it's not unusual. If we get something less than 0.05, it is unusual. That's kind of the only difference with these is throwing in that vocab. And again, we've gone through these formulae in class, so here I'm just kind of sketching them out for you as a review. All right, so key takeaways from proportions. Our sample standard deviation, so that's what we called S sub P or sigma sub P. I'm going to use S just so we notify it's a sample. The mean sampling distribution of P is P hat. So meaning when we work with a sample, we signify it as P hat. Going down here is the sample size increases. So we talked about this in class. Anytime our n gets bigger, so as n goes up, our sample standard deviation actually goes down. So the bigger our sample, the smaller our standard deviation gets. Conversely, if it gives a really small sample, our standard deviation is going to not decrease as rapidly. So big sample, smaller standard deviation. And the last one, are the population and sample proportions always going to be the same value? Hopefully by this point, having done all of our work with randomization and simulation, we see that they're not always going to be the same. They're going to be close, but they're never going to be exactly the same. Okay, I'm going to do one more example here, and then we'll go ahead and jump into the practice. Okay, so first off, let's jump to the next slide. There is some typos here. So this said knock. Originally, it should say the word known, as well as in this slide. So this should be the word known, not knock. My bad on that one. And then here, it said mean something. It should say, oh no, this said, I forgot what it said, to be honest with you. But this should be the word mean. So for each of these parts, change whatever incorrect word I had there to the word mean. Okay, those are all the typos that I've caught thus far. So let's go ahead back to the previous slide and get started. So I threw this in here, S sub x, that's the notation we'll use. I want you to have this other one here as a note because some textbooks utilize it, but we'll use S with an X. So we're either going to use S with a P or S with an X to signify it's from a sample and whether it's a proportions or a means problem. So we have a machine used to fill, wow, there's another typo, used to fill containers with protein powder has a known standard deviation of 0.52. The goal mean fill volume is 48 ounces. So step one, we know we're dealing with a mean here, right? Because we've seen mu, we see that we're measuring things, right? We know this is a quantitative thing. It's not a proportion. So when we deal with means, just as a review, our number line of reference, we utilize negative 10 to the 99th to symbolize negative infinity, and positive 10 to the 99th to symbolize positive infinity. All right, step one, describe the sampling distribution of x bar, the sample mean fill volume, and then we're also going to go ahead and throw in the standard deviation in this part as well. Key idea is we're dealing with 25 such containers. So our sample mean, we leave it the same as the population. And then for our sample standard deviation, we're going to utilize this formula here. So I'm going to take what I'm told of that 0.52 and divide it by the square root of n. So here it's 25. And again, depending on your calculator, you might do this a bit different, but for mine, I'm just going to type it all at once. So I have 0.104. So nice 3 decimals there. So that's describing our distribution. This is what we're going to be working with for the remainder of the problems. All right. So I'm just going to go ahead and write that down so I remember it. Okay. So for this first one, we're going to go with the probability that a random sample of 25 such containers is more than 49.5. I put some space in here. There we go. Okay, so more than 49.5. Okay, if we think about this, right, that means 49.5 is my lower bound. Hold on there. There we go. All right, so if I'm thinking about my normal CDF here, and again, we've done a bunch with this in class, so this is just meant to be a review. If you missed it, if you we've seen these all before. So I want more than 49.5. So that's my lower bound. Upper bound, again, we're dealing with mean, so it's positive 10 to 99. We had 48 for our sample mean and 0.104 for our sample standard deviation. Here, oh, also I changed all these from 20 to 25. My bad, there was a good chunk of typos. So it doesn't really make a difference. The only thing is we'd have to do, if these were different numbers, is we'd have to consistently recalculate our sample standard deviation. So I just changed it to match the last slide. Okay, this one we're looking at less than 42.5, so it'd be a normal CDF because it's saying to find a probability. So less than, I would do negative 10 to the 99th. Good to go there. And then lastly, the between problem. So key idea here is we're looking at, is it unusual? What might we conclude? So this is looking for your interpretation here. So if I got something that was unusual here, I'd be looking at something, again, less than that 5%, so less than 0.05. What might you conclude? So in this scenario, we're talking about a machine filling protein powder. If I got something that was really unusual on the low end, I'd say maybe there was a clog in the machine. Maybe it wasn't, that would be the best thing. Maybe it just wasn't pouring correctly. If I got something that was really high up, I'd say it's pouring too much, right? So if it was really unlikely and it was really on the high end, it was just pouring too much. Maybe the containers weren't made right, whatever it may be. And if it was something that's not unusual, then the machine's working good, right? So if it's something that says a probability of greater than 5% or greater than 0.05, that means the machine is working as intended. All right, so hopefully that got us caught up on all these notes. What we'll be doing in class, as far as practice problems go, is we're going to go ahead and work through of our practice. We have 20 problems. We're going to work through numbers 1 through 4 together in class. So just kind of working through each of those things and seeing how that works for us. All right. Hopefully this caught you guys up and we're all good to go. I never know how to end these videos, so this is the end.